Yeah, I started recording. Okay. I'll share my screen now. Just a minute. Is my screen visible to all?
Yes, sir.
Yes, sir.
Okay, okay, very good, very good. Just a minute. Yeah. Good evening, everyone. I'm Jashuran, and I'll be your tutor for this course, Basics of Material Science and Characterization. Welcome to the NPTEL live sessions for GATE aspirants. And my voice is clear, right?
Yes, sir.
Yes, yes. Thank you. So, as I
Yes, sir.
thank you, guys. As I mentioned earlier, um, yes. Actually, the recording is going on. Just a minute, I'll verify it. Yeah, recording is going on. Yes. Thank you. So, as I mentioned earlier, in case you have any doubts, please stop me in the middle of the class and you can ask me. I'll do my best to clear your doubts. And in case I'm unable to clear in this class, I will look into it and I will surely clear in the subsequent class. So let's go to the course. So today it's going to be a introduction class. And just a minute, I'll turn on the pointer. Yeah, okay. So what I'm going to do is, I'm going to give a small introduction, and the prime objective of this particular course, okay, that is the basics of material science and characterization, is to train the students to understand the basics of material science and material characterization. So if anyone is planning to write GATE ME, MT, that is mechanical engineering, metallurgy, production and industrial engineering, or especially engineering sciences, so I believe this tutorial, this set of classes will be useful for you. Um, so this course will provide a platform for students to venture into the field of research in metallurgy, material science, and manufacturing. I guess somebody has unmuted. Can you kindly mute, please? Thank you so much. Also, it would help students to go into the industry side as well, not just research, but also to the industries and to startups, which is pertaining to the field of metallurgy and production engineering. Because material science is still not yet that much developed in India, but soon it will be very well developed. But as of now, metallurgy is well established and so is production engineering, and I believe this course will give you a very good edge such that you will be able to enter into these industries. So this will be the course content. I was told that I have to take 6 sessions, a total of 6 classes, and I will do my best to cover all of what is displayed over here. So basically, this is more or less metallurgy, but I will do my best to add some semiconductor elements also, and I will also try to introduce you into the aspects of material science, so that you guys can be prepared for not just mechanical and production, but also for engineering sciences. So today we are going to just look at the fundamentals of metallic and semiconductor elements, or say metallic and non-metallic elements. And then for the next session, we will go for Miller indices, crystal imperfections. Then we will go for constitution of alloys and phase diagrams. Then we will go for ferrous, then non-ferrous, and finally we will end with XRD theory and problems. Okay, so what are the parameters that one should consider while selecting a material for engineering applications? So all of it is given over here. Other than what is displayed over here, can someone tell me, what parameters can be considered while selecting materials for the engineering applications?
economics, availability.
Yes, excellent. Economics, wait, I'll write it down. Okay. Sorry, just a second. So you said, okay, just a second. Oh, sorry, just a second. Yeah, oh, something's not right. Just a minute, guys. It was working fine. What happened? Okay, sorry guys, some interface issue, I guess. So, okay, as you were saying, economics and availability. What else? Anything else?
Properties of materials.
Yes, properties of materials. Very good. Anything else? Okay, so here you have seen the most important thing that we should consider, right, is the properties, right? Such as the strength of the material, ductility, formability, texture, hardness. So all of this are, the external parameters. Like when you subject a specimen to external loading and testing. So all of this are most probably destructive tests, most of them, except hardness. Maybe we have Vickers hardness and nano indentation, so it won't be much of a destructive test. But the rest may be destructive. And also um, uh, processing strength, ductility, fracture properties, and likewise we have a lot of properties that we should consider while selecting the materials for engineering. So, what we can do as material scientists is that we should select an existing material which is perfect for our application. Not only that, it should be suitable for machining, forming, and joining. As our friend said, economical, available, and it should give the output that is required. Designing is one phase, but manufacturing is what makes it come to practice. So, the most fundamental thing for designing and developing the new alloys and new materials, or even creating the existing materials, is to know about the material. And most probably we'll be dealing with metals in this course. So we should know about the phase diagram. The phase diagram of the metals, the alloys that we are going to use. Also, uh, you might have already known about the various types of phase diagrams, such as binary, ternary phase diagrams. Also, we will be going to other aspects such as the crystal structure, the atomic bonding between the various atoms in the particular element, and also we will go for the defect structure, the micro and macro structures. So microstructure means it is, as the name suggests, things that are not visible to the eye, not necessarily in the micrometer range, but if something is not visible to the eye, we kind of call it microstructure. Usually in metallurgical terms, it is something below 1 millimeter, because anything below 1 millimeter we can't see properly. It's not observable, and you have to use specialized equipment such as a microscope to view it. That's why we call it as a microstructure. So defects are, there are the various defects such as the Frenkel defect, Schottky defect, and the various other grain boundary defects are there. We will discuss all of these defects in the coming class, and also the macrostructure. Macrostructure is anything above 1 millimeter. So what we can see with our naked eye. So that is the macrostructure. And most of the properties that we see over here pertains to the macrostructure, right? So whereas things such as corrosion, detailed study of corrosion, we go to the microstructure aspect. In even formability, we will look at the microstructure. Then also, there are different scales in the microstructural world, and if something is in between 10 power minus 3 to 10 power minus 7, we call it grains. If something extends beyond 10 power minus 7 to 10 power minus 8, we call dispersoids. If it's below that, say 10 power minus 8 to 10 power minus 9, that is the nano range, we call them precipitates. And then from 10 power minus 9 to atomic level, 10 power minus 10 is angstrom, that is atomic level. So these particles, we will call them as either atoms or dislocations, or the spacing, the planar spacing. So first, let us go to the fundamentals of metallic and non-metallic materials. Some are semiconductors, some are metalloids, and some are halogens and gases. We'll go to them in the detail. First, we'll be dealing with the periodic table. As you all know, that the periodic table has a total of 118 elements till now, and it is like classified into alkali metals, alkaline earth metals, transition metals. Then we have the inner transition metals, that is the lanthanides and the actinides. Then we have the basic metals, metalloids, non-metals, and the halogens, and finally the noble gases. So guys, for grade, please read, please keep these two columns, column number 1, column number 2, or let's say group number 1, group number 2, as well as group number 17 and 18 on your fingertips, because questions may be from these 4 columns. And then another thing is the metalloids. They are actually they are the type of materials which are between metals and non-metals. So they exhibit some characters of both metals and non-metal. That's why they have been placed under this metalloid category. And if we would take just one element of this periodic tables, let's say carbon, and we look at what is written, we can find that the atomic number of the particular element, the symbol, the name, and the atomic weight is given. Usually this is the order in all periodic table. So whenever you see the periodic table, the first will be the atomic number, second is symbol, then name, then finally you will have the atomic weight. So you may ask what the atomic number is. The atomic number is the number of protons that are there in a particular element. So also please and also the atomic weight is the total weight of the atoms, that is the weight of the electrons, each electron, the weight of the protons and the neutrons. Everything put together is the atomic weight, and its unit is in AMU, or atomic mass units. I want everyone to note down these two parameters, that is the mass of the proton and neutron. So these are all standard values, they are not going to change. Most probably they will be given in your gate, but for safety purposes it is better to remember these values. So the mass of each proton and neutron is around 1.67 into 10 power minus 27 kilograms, and the mass of each electron is 9.11 into 10 power minus 31 kilograms. Mostly mass of proton and neutron won't be asked that much in gate questions, but the mass of electron is very important. It will be asked in almost all the questions, especially pertaining to characterization. Next, let us consider the interactions between two atoms. Okay, so let's just take two random atoms and then bring them together from infinity, right? So what happens is, when you bring these two atoms from infinity close together, there will be some energies that are acting upon it. Okay, and what are they? One is repulsive energy and the other is attractive energy, right? So what will happen is, you just have a look at the graph over here. When the atoms are, at a far away distance, there is no, they are completely neutral. There is no, changes that are happening on the surface of the atom. But as they come closer and closer and closer together, what you see is there is an increase in the attractive force. And the reason why there is an increase in the attractive force is due to the presence of opposing charges. You see, at the core of the atom, we have the protons and neutrons. Neutrons do not have any charge, but protons have positive charge. They are at the core and they exhibit nuclear attraction. Also, they attract the electrons towards them. What happens is, when the atoms come close together, the protons of this particular atom will start attracting the electrons of the other atom. As a result, what happens is there is a huge attraction at a particular point. So you may wonder why, like, it can just continue attraction, right? I mean, why is this sudden drop over there? You may wonder. The thing is that once the electrons, like the protons start attracting the electrons, what happens is, it is a mutual process. It's not, one atom attracting the other. Each atom attract the other one. So since it's a mutual process, what will happen is all the electrons will start coming towards the surface, and this will cause a repulsion. So what will happen is, beyond a particular limit, the atoms won't come close together. If they try to come, there'll be a huge repulsive energy which will push them away. So this particular point where, there is heavy attraction, okay, that is called binding energy. So it is at this point that the atom will be equidistant, at equilibrium towards each other, instead of any charge imbalance. So does anybody have any doubts till now?
No, sir.
Okay, I hope my wordings are clear. So yes, thank you. The height or depth of the curve is bond energy. Bond energy and binding energy, they are the same thing only. Okay. So next, let's take a look at the atomic bonding further. The melting temperature is large if the bonding energy is larger, right? So it is pretty obvious, right? If the atoms are bonded together closely, tightly, it's hard to break them, right? So what happens when we increase the temperature? When we increase the temperature, what will happen is the bonds between the atoms, okay? So there are several types of bonds, we will get to that soon, but those bonds will be severed, right? So the thing is, if the bonding energy is very, very high, then it will not so easily be broken when the temperature is increased. So if the melting temperature is, if the bond energy is high, the melting temperature will also be high. Also, if the bond energy is high, the elastic modulus also will be high, because if the material is rigidly packed, right, it's not so easy to break it or bend it or deform it, right? As a result, if the bond energy is high, the elastic modulus will also be high. So please guys note these lines, because they may be asked as 1 mark suddenly. And also please note this formula. It is the basic formula, that is Young's modulus is equal to stress by strain. So the stress is over here, that is force by area, and the strain is here, change in dimension by original dimension, and in our case it is change in length by original length. So is there any doubt so far? The diagram that you see over here is similar to what we saw over here. It's not any different. Are there any doubts?
No, sir. But I have a question, sir.
Yes.
If repulsive energy would be high, then what would it be? Like, would the distance between pi and sigma bond would be greater value?
Oh, okay, okay. So the thing is, like, we will not go as to what type of hybridization takes place, like, whether it's a pi-pi interaction or a sigma-pi or something like that. But the concept here is that we are, what will be happening is that due to more number of electrons on the surface, there will be a repulsive force. This repulsive force will not push the atoms too far away. It will keep them fixed at a particular point. So I hope you get it. Like,
Yes.
so this is the point of equilibrium. Okay, the point that you see over here, right, where there's maximum binding energy. That is the point of equilibrium.
Sir, would it be in a homogeneous way? Like, the distance would be the same for every particles or like that?
Yes, see, the thing is, if you are dealing with crystals, then you're right. It will be homogeneous. But if you are dealing with other materials such as ceramics and polymers, then it will not be as homogeneous as metals. Like, their range of order will be very, very short. So there will be only few atoms which are regular, then the rest of them will be irregular. So
Okay, sir.
I hope I'm clear.
Yes. Thank you, sir.
Thank you, thank you. So next we'll come to this term, coefficient of thermal expansion. So the coefficient of thermal expansion is nothing but the strain, which is equal to the coefficient of thermal expansion into the change in temperature, or we can say that the strain is directly proportional to the change in temperature. That is, if the temperature is either increased or decreased, it is going to cause an internal strain in the material. So that is the concept of the coefficient of thermal expansion. So it is usually denoted by alpha. Please note this formula. You may be having problems from this particular formula and topic. So let us now go to the types of atomic bonding. There are predominantly two types of atomic bonding. One is primary and the other is secondary bonding. So secondary bonding is very, very weak. It is also known as van der Waals bonding, and we will not be covering that deeply in our tutorial. Whereas we will be going deeply into the primary bonds. So we have covalent bond, ionic and metallic bond. So in covalent bond, the electrons are shared to make the bond between the atoms. So covalent bond is actually one of the strongest bonds. And if you see over here, can anyone identify what element this is or what molecule this is?
Methane.
Exactly.
Methane, sir.
You're absolutely right. It's methane because there's a carbon atom and then there are 4 hydrogen atoms. See, the carbon atom is having 2 orbitals, s orbital and the p orbital. And at the p orbital, what is happening is the electrons of the carbon atom, that is the valence electrons. So carbon has 4 valence electrons, right? That is being shared with the valence electron of hydrogen, and that is causing the bond. You may wonder, like, electron is supposed to cause a repulsion, right? How on earth are they sticking together? That may be a question. But the thing is, again, there is attraction. We are many times forgetting the central nucleus that is there. The nucleus consists of protons, right? The protons have the positive charge. And this positive charge, protons, will attract the electrons of the opposing element. And that is what causes this particular bond. So the shared electron from hydrogen, you see, is actually the electron of hydrogen which is attracted by the proton of carbon. That's why it is sticking over here. Likewise, if the electron of carbon is sticking with hydrogen, then it is due to the attraction of hydrogen's proton on the electron of carbon. So I hope you guys understand and understood the concept behind covalent bonds. Am I clear?
Yes, sir.
Yes. Thank you. And then next, yes.
सर एक बार 2 स्लाइड पीछे एक बार देखना था
This
वो
one?
अल्फा वाला.
Oh, this one. Okay. Before.
ओके जी सर.
Yes. 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 Tell me.
नहीं सर वो देख लिया जो देखना था.
Oh, sure. Sure. Okay. Okay. If anyone wants to take screenshots, also it's absolutely fine. No problem. Um, can I proceed?
Yes, sir.
यस सर.
Thank you. Thank you. Okay. So yeah. The second type is ionic bonds, and now I think I shall go faster because time is running out. So the bond where one atom loses one electron while the other atom gains the electron. Now you may wonder, like, what is the difference between this and the previous case, covalent electrons? Covalent bonding. In covalent bonding, the electrons are actually shared. In the sense, if carbon, if an electron of carbon is going to interact with hydrogen, an electron of hydrogen will also interact with carbon. So that's going to happen. Whereas in this case, that is not, going to happen. What will happen is the electron from one will go and will be attracted to the other. That's it, not the other way around. The reason being, chlorine is highly electronegative, which means it can easily attract electrons. That's why when you bring sodium and chloride together, chlorine will just attract the valence electron of sodium, and that will cause the bond. There won't be any mutual sharing, rather it will be the attraction of sodium's electron towards chlorine's side. So this is ionic bond. And another thing is ionic bond occurs between metals and non-metals. So you have to note this point. Ionic bonds occurs between metals and non-metals. Whereas covalent bond, it usually occurs between polymers or non-metals, and especially carbon atoms. Carbon atoms are the best example for covalent bonds. And also electron transfer creates the ions, right? Just imagine, we have a sodium atom. If we remove an electron from it, what happens to it? It becomes an ion, right? Same thing. And the law that is happening over here is Coulomb's law. That is, opposing charges attract to each other. And this is just a rough reaction. The sodium, when the chlorine comes in its vicinity, it loses its electron because of the high electronegativity of chlorine, and the lost electron from sodium gets attracted to chlorine. As a result, sodium becomes positive and chlorine becomes negative, as it has gained an electron and sodium has lost an electron. And once this process has happened, they will tightly bond together and become neutral, called sodium chloride, which we also known as the common salt. Another thing is, this is non-directional. So it usually, won't be in a particular direction. And magnitude in ionic bonding is equal in all direction. So the magnitude will also be equal. And another thing is, ionic solids are brittle, and any strong repulsive forces will break the crystal apart. So I believe you already know about what brittle materials are. So brittle materials means if you give a force, the material will automatically break. So the reason is because similar ions are very close to each other, right? Because just imagine, there's sodium chloride, alternatingly they are just arranged, and all you have to do is just slightly displace them, and then they're immediately broken. So that's what happens in ionic bonds. I hope I'm clear. Is there any doubts?
सर मतलब जो नमक का एक पार्टिकल मतलब वो लेंगे, वो एक क्रिस्टल हुआ या फिर उसके अंदर भी क्रिस्टल है?
I'm sorry, actually, I don't know much Hindi, so if possible, can you tell in English if it's okay?
Sir, if we take a particle of table salt or common salt, then that is crystal or not?
That is a crystal, yes. That is a crystal, actually.
Okay.
Because, if you would look, I mean, from the naked eye, it wouldn't be very visible, but if you look at it under a microscope, you can clearly see that, the atoms are well arranged. So, it is actually a crystal.
Okay, sir. Okay.
Yeah. Next,
Sir, could you
yes.
tell
Yes, tell me.
ionic bond electrophile or nucleophile bond?
Actually, here the it's actually electrophile only because chlorine is attracting the electrons, right? So it's more of
Yeah.
a electrophile. Yeah.
No, sir, actually, is it a way more electrophile or nucleophile?
Sorry, I didn't get you. Are you asking about the chlorine?
No, no, no.
Uh,
Actually, for every reaction,
uh,
while the bond is happening, then is it sometimes more occurs the electrophile bonding or nucleophile bonding?
Mostly here it will be electrophile bonding,
Okay.
because the electrons are attracted towards the nucleus, right? So uh, it's more of an electrophile bonding.
Okay, sir.
Yeah. Next, we have metallic bonds. So in metallic bonds, the prime advantage is free electrons. You have a lot of valence electrons. And since there are so many valence electrons, they will be freely moving on the surface of the metal or material. Since you have so many free moving electrons, they are able to conduct electricity and also they are able to conduct heat. And since there are so many electrons, we call it as sea of electrons. And they are continuously moving, they are not in a single place. That's why when you give a charge, they will immediately go in a particular direction. Also, another thing is metallic bonds are malleable and ductile. So these are exclusive qualities only for metallic bonds. This is not available in either covalent nor in ionic bonds. Malleability means this particular metal or metals, they can be hammered into thin sheets. Ductility means metals can be made into thin wires. And since time is running out, I'll go a little faster. And this is the summary of the primary bondings. Ceramics are either ionic or covalent in bonding. So you may get this in 1 marks. Metals are definitely metallic bonding, nothing else. Whereas polymers, you have a combination of both covalent and secondary bonding. Among their own chains, right? Carbon chain, it will be a covalent bonding. But when two chains come close together, it will be a secondary bonding. So I believe we have already seen these properties. For ceramics, there will be a large bonding energy. That's why you cannot easily, melt ceramics. You would have seen if there is any ceramic bowl, if you try heating, it means it will not melt so easily. Same thing there. Young's modulus is very high, meaning they are very stiff. They are brittle, but they are very, very stiff. You cannot change their shape. And also they have very small coefficient of thermal expansion. That is, if you heat them, they don't expand so easily. If you take metals on the other hand, it has a moderate melting temperature compared to ceramics. Ceramics, if you want to melt, you have to go all the way, I believe, to 2000 to 3000 degrees centigrade to melt them. Whereas metals, you can start by, I think aluminum is, at lead, it can be melted around 330 degrees centigrade if I'm correct. And aluminum, it starts melting around 660. So likewise, if you are melting steel also, it will be in the 1700 range maximum or 1900. So that's pretty moderate compared to that of the melting temperature of ceramics. Also, it has moderate Young's modulus in the sense you can, you can bend it or deform it easily compared to that of ceramics. Also, if you heat it, it easily, expands. So it has a moderate coefficient of expansion. And polymers, they have directional property, right? And the thing is, depends on the polymer chain, the material will, the behavior of the material will vary. And you will have secondary bonding domination because you'll have multiple chains growing haywire here and there, and the bonding between them will be pretty weak. And since the bonding between them is weak, if you give a slight temperature, say around 200 or 250 degree, any polymer will melt. I don't think polymers can withstand a temperature of beyond 200 degrees centigrade. And then when it comes to Young's modulus, they are very, very malleable. You can, you have seen plastic, right? You have used plastic buckets. You can easily bend them and twist them and whatever. And also they have very large coefficient of expansion. If you heat them, they immediately change shape. They immediately expand. Next, we have the type of arrangement. I won't go into the details. I'll just tell them what they are. Initially, there is no order. No order means gases, right? Then there is short range order. Short range order, usually they are liquids or sometimes glass. Okay, so this what you see over here, this arrangement is a glass arrangement. Then you have long range order. They are crystalline materials. Short range orders are usually amorphous materials, and if there is no order, it is definitely a glass. So all the materials that we are going to deal with will come under the long range order. Next, okay, we have the type of atomic arrangement. So we have single crystals, then we have polycrystalline arrangement and amorphous materials. If we take just single crystals, it will be one giant crystal. That is, the whole thing will be just a single unit cell, right? There won't be any grain boundaries. If you look under the microscope, it will be clean. It won't be like this. This is a polycrystalline material. When you look at single crystals, they will be clean and they exhibit a lot of good properties. So maybe in the coming classes we will go into the details. Some of the best example of single crystals are computer chips, turbine blades, and they have perfect directional properties, excellent directional properties. When you come to polycrystalline materials, most of the metals and alloys and ceramic materials come under this category. When you look under the microscope, you'll find a lot of grains and grain boundaries. And they, though the order is a long range order, the thing is, each long range order will be in one direction. That is why you are having all these small grains, right? But when you come to amorphous materials, there will be absolutely no order at all. You won't even find these sort of grains. Like when you look under the microscope, it will be very, very irregular. So that is amorphous materials. We'll quickly go to the chemical properties. See, most elements are metals in the periodic table. So 88 elements to the left of the metalloid line. We saw the metalloid line, right? So most of them are metals, and they are predominantly on the left side, and the non-metals are found to be on the right side of the metalloid line. So if you would compare the chemical properties of metals and non-metals, the metals, as we already know, since they have the sea of electron, they easily lose electron. Whereas non-metals, they tend to gain electron, because if you see the periodic table, uh, see, these materials here are highly electronegative. That's why they tend to gain electron quickly. Whereas here the electronegativity is very less, so they tend to lose electrons. Okay? So, yeah. Next, since metals easily lose electron, they corrode easily, right? Corrosion is due to just loss of charge, right? Loss of electrons, which will cause the metal to go back to its ore state. Like it will become oxidized and it will go back to its ore state. So in metals, it will easily happen, but whereas in non-metals, especially ceramics, they do not corrode so easily. Next, if you look at the physical properties, like physical means just with the naked eye, if we look, we can find all of them. One is non-metals. They have no shininess, no luster. They are poor conductors of heat and electricity. They have high density. They are very heavy for their size. They have very high melting point. They are ductile and they're malleable. If you come, sorry, I'm so sorry. Non-metals are not ductile and they're non-malleable. I'm sorry. I made a mistake here. Um, in metals, they have good luster. They are good conductors. They are they are actually in lower density compared to that of non-metals, especially ceramics. Then their melting point is also low. I made a mistake here. I'll have that corrected. And these things can be ductile, that is drawn into thin wires, and malleable, hammered into thin sheet. You may be having this in your match. Next, we have a problem. I thought I could make you guys work out the problem, but due to the lack of time, we'll just go into it. Say, we consider an element of mass m with a Young's modulus of 70 gigapascal and a coefficient of thermal energy alpha, that is 23.1 into 10 power minus 6. We have to find the strain in the material when it is heated from room temperature to say 200 degrees centigrade, and we have to find the stress acting on the material. So this is actually, this is not a gate question, but the possibility of this being asked as a gate question is high. So you remember we saw a formula for coefficient of thermal expansion, right? I mean, not coefficient of thermal expansion, rather strain. Does anybody remember that? We just saw.
Alpha delta
Yes, alpha.
alpha delta T.
Yes, alpha delta T, which is equal to
150 here.
strain, exactly.
150.
Yeah, strain. And also another thing is when you're dealing with temperature, it is better to convert it into Kelvin, so that there usually won't be an issue. So this is the solution. First, to find the strain acting on the material, the formula strain is equal to the thermal conductivity into delta T, right? So we just substitute it directly. This is 23.1 into 10 power minus 6 into the delta T, T2 minus T1. So we are getting the strain as 4.04 into 10 power minus 3. Next, we want to find the stress. We already know the strain, right? So what do we do? How do we find the stress?
Young's modulus is one.
Exactly. Young's modulus, stress by strain. We find the stress. So everyone is clear, right? Nobody's having any doubt in this problem, right?
Yes.
Thank you. I'm sorry I have to rush because of time. So we'll briefly discuss about packing. As I had already mentioned about this particular energy diagram. So at this particular point, the atom will be stable, and this is a particular property of metallic items, because everything, solids which are very closely packed, especially metallic solids and crystals. If materials are amorphous, they will be yes. Somebody raised your hand. Okay, I'll try to end this soon. So crystals are densely packed, whereas amorphous materials are very loosely packed. Okay, and in the next class from 7 to 8 p.m., my colleague will explain in detail regarding all the materials in packing, and also about the this thing. Atomic packing factors and everything. So what I will do is I will just discuss with you
So,
this
what is amorphous material?
amorphous material. So
Yeah.
amorphous material are usually materials which are very irregular in their pattern. So they do not have a long range order. Long range order means they do not have this regular pattern throughout. So you see, here the pattern is very regular. You have a hexagonal closed pack structure, I guess. No, this is silicon. Silicon is a little different, but here it's regular. Whereas non-crystalline means, or amorphous. Non-crystalline is also known as amorphous. It is irregular, right? So amorphous materials are
I understand.
irregular. Yeah.
Okay, sir. Thank you.
Okay, so now we'll quickly rush. Just give me 3 more minutes. I'll finish the essential part. So metallic crystal structures. So we can stack metal atoms into, either a hexagonal shape or a cubical shape, yeah, a square shape in 2 dimension to, accommodate them in the maximum way. So can you tell me which of these two uh, has minimum empty space? Is it a hexagon or is it the square? This is in the case of a 2D.
Hexagon, sir.
Hexagon.
Hexagon, sir.
Yeah, that's what we would think, but the answer is actually the square. I'll tell you. So I'll just explain this and then I think we can end it here, because after this everything my colleague has already prepared, so she will explain better. So the maximum theoretical packing of a 2D system, so this is a GATE 2009 question. If we take this square system, right, I believe you guys already know the formula. Packing factor is equal to the area occupied by the atom divided by the area occupied by the whole unit cell. Okay. So packing factor is equal to, in our case, what is it? The area occupied by the atom is nothing but the unit cell, number of atoms in the unit cell. What is the number of atom in the unit cell? We have this unit cell. There are 4 atoms in the unit cell, and each atom is in contact with actually 4 more. So this, if we take this atom, it's in contact with 1, 2, and then there will be another one here and here. So 3 and 4. You take this one, 1, 2, 3, 4. So 4 into 1 by 4. So this becomes 1, and if we simplify this, the AA gets cancelled and we get a theoretical packing factor of 78%. Right? When you come to hexagon, the theoretical packing factor we get is only 30%. So the square, in the case of 2D, please remember, in the case of 2D, the maximum theoretical packing is in a square system and not in the hexagonal system. When it comes to 3D, then hexagonal closely packed will have the maximum theoretical packing along with FCC. Okay. Here also we did the same thing. The number of atoms into the atoms which it is in contact with, right? Coordination with, 6 into 1 by 6 into the radius of the atom, the area of the atom divided by the um, area of the hexagon. That is the area occupied by the unit cell. This will give you the answer as 30. Okay, since time is run out, guys, let's stop here. And everything that we are going to see, right? Metallic crystal structures, the simple cubic, body centered, edge centered, face centered, everything will be explained by my colleague in the 7 o'clock class. So I'm so sorry for whatever happened today, the computer that got disconnected in the middle. I'll make sure that doesn't happen again. So thank you so much for joining, you guys. Have a nice day. If you have any doubts, you can please ask me. Are there any doubts?
No, sir. Thank you.
Yeah, thank you so much. Yeah. We'll
सर
meet.
सर वो हेग
Okay, sir.
Yes, please tell me. Yeah.
सर हेक्सागन पैकिंग में जो एरिया ऑक्युपाइड, एक बार वाला स्लाइड खोलिएगा.
That one, huh? Previous. Just a sec. Uh, just a sec. Yeah, this one, right?
हाँ सर. सर यहाँ PF इक्वल टू 6 into 1 by 6 की बजाय 6 होगा सर यहाँ पे वैसे.
So if we take this hexagonal close pack structure, right? We have
हाँ
these 6 atoms, and then we have each atom is in
1/3 पोर्शन हो रहा है उनका, प्लस एक अंदर का है, तो ओवरऑल हमारे 3 हो रहे हैं सर एटम.
no. See, that is 3D system. I believe you're talking about HCP, right? Hexagonal
No,
close
sir.
packed.
सर मैं इसी की बात कर रहा हूँ, मतलब कि इसमें 3 हो रहे हैं ना,
Uh,
एक सेंटर वाला और सिंस 120 डिग्री एंगल है,
हाँ,
मतलब इनके बीच में, तो 120 डिग्री 120 डिग्री 120 डिग्री तीन मिला के एक एटम बनाएंगे।
oh, okay. So
तो
3. Oh, so you're
थ्री
saying there's 7, right?
नहीं, अरे नहीं सर, मतलब तीन ऊपर के और तीन नीचे के, ये 2 एटम हो गए, और एक बीच का 3 एटम हो गए।
So
सर
1.
30 पैकिंग थोड़ी सही नहीं लग रही है, 30 इतनी कुछ ज्यादा ही कम है।
Sorry, can you tell it in English? I'm unable to understand.
सर 30% इज बहुत, मतलब लेस लग रही है, बहुत कम लग रही है।
Okay, no,
इससे
actually,
ज्यादा।
no,
Sir,
actually,
he was telling that boundary at hexagonal that one atom has occupied almost 30 मतलब 33% तक occupied है हेक्सागोनल का।
mm-hmm.
तो ऐसे तीन मिला के एक एटम होगा, और दूसरे तीन मिला के दूसरा एक एटम होगा, और बीच का एक एटम, और मतलब ये होकर कुल तीन एटम होंगे। और वो बात उसको समझ नहीं आ रही, ये कहना चाहता है।
Okay, so I'll just re-verify this in the next class, because like when I saw it was 32%, so that's why I think, but I'll have it checked again. I'll definitely have it checked. So thank you for pointing this out, guys. So yeah, and also it would be good if you let me know in English, because I don't understand Hindi. So
ओके सर, ओके।
sure. Okay, I'll re-verify this one. Sure. Yeah. Anything else, guys?
Sir, the next class by you, sir.
No, no, no. The next class is by my colleague actually. So that's in another link, in the
Yes,
same
sir.
page, NPTEL Gate portal.
Yes, sir. Thank you, sir.
Thank you so much, guys. Thank you.
Can we leave, sir?
Yes, yes, you can leave. Yes, thank you so much. Yes.
Thank you, sir.
Yeah, bye. Thank you.